Okay, so my name's George Brown. I work as a sysadmin on the Phoenix cluster at CSCS. It's a cluster for the WLCG grid, and we operate as a tier 2 within Switzerland. So here's a picture of the cluster. This is in our new data center in Lugano, as Thomas Schultes was talking about earlier this morning. As you can see, it's contained within an island within a data center. So this is slightly different from the larger systems Thomas Schultes was talking about earlier. We still use water from the lake to cool the systems. However, the more conventional systems or systems within islands like this are cooled from within a closed loop within the data center. So water comes in from the lake and directly cools systems such as the crays, and then also cools the closed loop for items in the island and the rest of the data center, such as conventional hardware like Phoenix. So as I briefly mentioned, Phoenix works as a tier 2 cluster for the WLCG grid. It consists of 1,264 physical cores. We use hyper-threading across all nodes, but that's the physical count, and 64 gigs memory per node. Storage is a bit different from other sites. We have a Scratch file system. This isn't very common within the grid. We're one of the few sites to do it, but it gives us a lot of efficiency, which I'll come to shortly. Just to say, most of the nodes within the cluster are Intel Sandy Bridge. We still have 10 AMD Interlagos nodes, but the vast majority is Intel Sandy Bridge twin squared units, as opposed to Pixelbox 1U units. So CHIPP is a client for us, the Swiss Institute of Particle Physics. So we have a somewhat business relationship with them. We need to provide them a system for the funding they give us, and we need to prove that system is efficient and cost effective in all areas. So as I mentioned with the Scratch file system, it leads to gains in efficiency. One of the more common things you would see in a grid cluster is local Scratch on a local disk. As the number of cores increases and the number of jobs you run on a single node, that quickly begins to stop scaling. So this graph is from the previous year. I don't have more up-to-date data, but the yellow line at the top is the efficiency for jobs run at CSCS, and you can see scattered around other sites and their efficiency. So where the yellow line is, we're about 1, and you can see lower CPU efficiency. So that's one of the main benefits of having the Scratch file system for us. This slide has already been gone, I apologize. So the main factors for us buying and removing hardware are pledges we make to CHIPP. So every year we pledge an amount in hpc performance on CPU and storage in number of terabytes. So we typically buy compute with 3 years warranty and storage for 5-year warranties. And then space and power is then another consideration. Within CSCS, we're fairly concerned about power, and we try to minimize our usage wherever possible. And as a sysadmin, I don't like having idle hardware in the racks. It's something that annoys me. So this is what our phases look like over time. So we just name our phases with a letter going up the alphabet, quite simply, and we go through time. So this may look a bit more understandable to you, so you can see different architectures. So originally, the Phoenix cluster was entirely Sun hardware. We now only have a few Sun machines left, and we have the vast majority on standard Intel or IBM hardware. So as you can see, the 10 AMD Interlagos nodes we have in the cluster are currently approaching the end of their lifetime, and we'll be looking at making a purchase of some new compute nodes in order to replace those. So you can see we have a cascading purchase routine where we have some old hardware we purchase and then we phase out. It's a rolling scheme. So in terms of the pledges I spoke about, you can see we pledge hpc performance, storage quantity, and as well as Scratch. So typically we try to be very conservative with our pledges. The reason being is we have to pledge in advance, so we can't guarantee cost. So if there's something like a fire in Taiwan or a factory goes down and the market price soars for a component, we still want to be able to make pledges that we've made to the CHIPP. So usually we end up exceeding the pledges every year, which CHIPP likes and we like as well. So you can see phase G is where we are now. You can see we've exceeded the current pledges. And then the next phases over the next 2 years, they differ on how much we buy in storage and compute. The reason being is warranty. So within 2015, we'll have some storage go out of warranty, which we'll need to replace with something that will be more dense than it was previously, so we grow more on storage. So the Phoenix cluster within CSCS is quite separate from all the other systems. So within CSCS, we have global file systems for users, apps, home. Obviously, the grid community doesn't use any of that. But we do take advantage of some of the centralized resources within CSCS to help offload admin work, reduce costs, and just make things more efficient. So one of the main ones is the InfiniBand network within the cluster. We have a network admin who administers the entire InfiniBand infrastructure across CSCS. This at times has proved invaluable for us because we gain an external perspective from the network. So he can view traffic coming in from switch in and out of the cluster, and we can monitor tightly within the cluster. So this has helped us debug some very odd issues we've had in a lot shorter timescale than otherwise would have been possible. A more recent addition is we have a new centralized NAS within CSCS. We would not have been able to afford this within Phoenix's budget. It simply wouldn't have happened. So currently within Phoenix, we're using an NFS mount across 2 DRDB machines. Obviously, we have to maintain that internally within the cluster. Outsourcing that, again, saves us admin overhead and just makes our lives easier as sysadmins. So the challenges we have within the cluster, as I said, we have to meet pledges and we have to meet them on time. So we need to make sure we have the new capacity installed, up, running, and tested within defined timescales. The more challenging aspect is storage and space. So as you saw earlier, we operate within an island. That island consists of 12 racks in total. As of today, we have 2 racks that are entirely empty. However, because we need to migrate storage and have as little downtime as possible, we have to have both new and old storage online at the same time. So we have to run a migration, then we have a brief downtime where we switch over the storage and bring up the new storage and present that to users. This is quite challenging, not only in terms of physical space, but also power distribution. So obviously we can't just have an entire rack full of compute. We don't have enough power within the rack to power that. So we have to carefully consider years in advance where we're going to place hardware and what other hardware we'll place in that rack ahead of then to make sure we can physically shuffle everything around. So in terms of that storage, the Scratch file system at the moment, it's coming to the end of its life. So this is one of the things we're going to be looking at replacing. The Scratch, it should be an easier migration. So there's no essential permanent data that we have to transfer, but we do have to install it within the rack, benchmark, test, and then bring online. The far more challenging aspect is our Dcache storage. For those of you not familiar with Grid, Dcache you can think of as a more long-term storage plan rather than Scratch. The problem with this is we have terabytes and terabytes of data in enclosures to migrate, and we need to have that both online at the same time, which takes up a lot of physical space. Now, unfortunately, we have a couple of enclosures which will run out of warranty at the same time. So we're likely going to have to phase them in blocks at a time. So one enclosure and controller at a time. We take the old one offline and then do another one. For sysadmins, that's a lot of racking, time, and waiting for us. So that's the most challenging aspect. Again, it's more of a juggling act in terms of things we have to do with space and storage. So once a hardware expires from its warranty, we move it into our pre-production environment, which is entirely consists of VMs. We just take the machine and we change it into a KVM host, and we run all our pre-production and testing within that environment. As such, when hardware becomes decommissioned from production, we move it into pre-production, and then we move whatever excess hardware we have from pre-production out of the cluster. That way, our pre-production hardware is kept rolling, it's kept semi-current, so for sysadmins such as myself, the performance is reasonable, and also the newer hardware has much better power efficiency than having old hardware constantly powered on within the rack. When we no longer have use for hardware within the cluster, we try and give it away to the rest of the physics community around Switzerland. This is particularly attractive with the Sun hardware. As I said, Phoenix originally was entirely Sun hardware. Obviously, with Sun's demise and Oracle's takeover, if you have Sun hardware within your cluster, and it's probably getting pretty old by now, so the idea of taking up a support contract with Oracle might not appeal to you, seeing as it can be very expensive. So we try and give our hardware away to other sites which are in more need of it. They can also make use of parts if they don't have to rack the full machine. So for instance, some sites may have different hard drives that are proven less reliable, or we have some slightly more reliable hardware and they can make use of it. The general idea being is we don't want to throw stuff into a landfill or just throw it away. We want to make sure it's having some kind of use. So I've tried to be quite concise on time there, but if you have any questions, I'll be happy to answer them.